Hello, I'm Patrick Alla from IPGP in Paris. I'm the newly elected president of IAVCEI. I'm delighted today to introduce you the union lecture by Paolo Papale from Italy. Paolo is currently research director in IUGV, the National Italian Institute for Geophysics and Volcanology. And sorry for your modesty, Paolo is one of the most brilliant volcanologists of his generation. He exerted various responsibility in Italy as coordinator of the National Program for Volcanic Hazards, for the also director of the Volcano division in INGV, also at the European level as president of the GMPV section of EGU, for instance. He will present us a talk today on volcanic giants and a number of questions of what we know, what we think we know, and what we cannot know. And prego Paolo, grazie mille. Ti ascoltiamo con piacere.
Thank you, Patrick. Good morning, everybody. When I was invited to give this union talk here at IUGG, I was really honored, and also I felt myself in trouble. And the reason is that volcanology is really becoming more and more a multidisciplinary science, and there is a so large number of exciting new results which are being achieved day after day that it was really hard for me to decide on what to focus this presentation. How do I go? Yep, okay. So this is just to show the kind of multidisciplinarity that volcanology hosts. We have developed something we call volcano geodesy, volcano seismicity. So if we were Snow White ourselves, contrary to the case for geodesy, we will be receiving from the dwarfs much more than giving. We take a lot from other communities, from physicists, mathematicians, geochemists, chemists, engineers, and so on and so forth, as you can see here. Today's control rooms at modern volcano observatories are high technological places where a long sequence of data, spatial and temporal data, are continuously collected, and that gives rise to pictures like this that we need to interpret, and sometimes we need to interpret them in nearly real time during a volcanic crisis, which is also triggering a substantial interest in machine learning and artificial intelligence, besides many other disciplines that we've seen. And also, we deal with very big problems with the society. This is quite an extreme case. That's Vesuvius on the background, and we have the city of Naples with about 3 million people that are virtually at risk of their life for a next eruption of Vesuvius, or the nearby supervolcano Campi Flegrei. So that forces us to have a lot to do with a long sequence of other experts like social sciences, and also experts in vulnerability assessment with whom we collaborate a lot. So in a way, we may say that if you are some sort of expert, you are invited to become a volcanologist. Yep. And also I was thinking whether I should focus this talk on some of the most exciting projects and ideas that we are pushing forward. This is something we are planning to do in Iceland at a volcano called Krapla, and KMT stands for Krapla Magma Test Beds. Here we plan to drill into the magma, open the well, let the well open and use it as a permanent infrastructure, the first magma observatory in the world. An open infrastructure directly inside the magma so that we can sample and monitor magma directly in situ, and also the conditions around the magma. And over the long term, we want to establish a series of drills and a series of observation points both on the surface and at depths, so to transform this in a real big infrastructure for the geosciences where we can perform real experiments on a natural system like this one. Maybe solicit the magma and measure what happens from below, from above, so to learn how to interpret the data from volcanic unrest. And also this has a lot to do with the geothermal industry, because part of it is also on the study of the possibility to obtain geothermal energy directly from magma, from very close to it. And well, this would be a big, maybe infrastructure in the geosciences, similar to those that other communities like the astrophysics or the particle physics already have. And some other major elements that I would like to talk about is what we are doing with astroparticle physics in defining a common roadmap for developing more and more our collaboration, which includes from neutrino to muon tomography applied especially at volcanoes, or new and more robust methods and techniques to measure gravity on the Earth and at volcanoes, of course, to putting together into a system some of the biggest infrastructures we have in the two communities. But at the very end, I decided to focus this on volcanic super-eruptions for reasons that I hope that will be clear at the end of this presentation. And I added a subtitle, which is quite well, ambitious, I would say, especially for the limited time. And so I will probably, what I'm going to say will probably have more to do with the last part, with a third of the questions below, what we may not be able to know. And we'll see that. And well, this is a hyper-concentrated selection of papers on supervolcanoes. I have to say that I'm not myself an expert on supervolcanoes. I was really looking for something else, exploring the database of volcanoes for completely different reasons, and I went through something that seems to me it is also relevant for supervolcanoes, and that's why I'm talking about that. That's something that often happens in science. You look for something and you find something else. Clearly I have to be immensely grateful to those people who dedicate a lot of efforts in building up databases that are extremely useful for all the community, stressing once again the relevance of big data, if there was a need to stress it once again. Okay, so first of all, what is a super-eruption? A super-eruption is an eruption, an explosive eruption, nothing else than that, but it's bigger. It's very big. We measure it in terms of the erupted mass or the volume of the erupted products, and the ejected mass must be larger than 10 to the 15 kilograms to define it as a super-eruption, or the volume must be greater than 1,000 cubic kilometers. And we call it M greater or equal or greater than 8, or VI equal to 8. These are two scales to measure the size of volcanoes. They are both logarithmic scales, so increase of 1 means 10 times larger. M is a continuous scale which measure mass. VI is a discrete scale which measure volume. And on the bottom, you can see on the left, no, what's the pointer? I don't know, maybe here? Is there a pointer? Everyone knows that? The other one, okay. So it's this one, okay. This one is the pyroclastic flow deposits from an eruption which is not a super-eruption. It is the Pignatube eruption in 1991, which has been one of the largest in the last century. And as you can see here, about 200 meters of deposits accumulated in about 3 hours. On the right here, we have instead the deposits of a super-eruption. That's the Bishop Tuff from Long Valley Volcano in California, which is nothing else than the same, just bigger. There is no scale here, but it is definitely bigger than that, and it's definitely bigger in terms of volume. The volume here, the total volume of the eruption will be a few hundred times larger than this one. Okay, so there is nothing really special in supervolcanic eruptions. In super-eruptions, The only difference being that they are extremely large as we've never seen them in our history, fortunately, I should say. So this is some of the explosive eruptions which have had some global impacts. The Mount Pinatubo eruption that we've seen before in 1991, which has been instrumentally recorded, and which produced an average cooling of the northern hemisphere, well measurable by 0.5, 0.6 degrees, and a size in the ozone hole 1 year later, which was unprecedented. And so this eruption here starts to have measurable global impacts. If we increase the scale, we go to Mount Tambora in Indonesia, which erupted in 1815, and which was about 10 times larger, and this had important global effects. It produced in Europe what was called a year without summer, a year without crops growing, severe famine, disruption of the crops. It caused massive migration, mostly toward the US. There was an estimated indirect casualties in Europe, which is just an estimate for that time, of about 100,000. Okay, so this was quite a severe global impact and substantial global impact. And the last one is the Toba caldera in Sumatra Islands, also in Indonesia, which erupted 74,000 years ago, and which is one of the largest explosive eruptions we know on Earth. And this was very large, as you can see here, and it has been controversially associated to the Toba catastrophe theory, according to which even man underwent a bottleneck and we survived by chance. So only few groups of men could survive, although that's highly controversial. Now we know that in other parts of the world, many groups of people flourished during the eruption, so it's not really true that, but this gives an idea of the size of the eruption and the size of its impacts. The global temperature cooled down by substantial amounts, 5-6 degrees, according to other models, maybe 10-12 degrees, and that lasted for some years, and very likely caused a volcanic winter during that time. And according to someone, this also was an additional factor favoring the starting of on about 1,000 years of global cooling on the Earth. So this is again to see the size of the volcanic eruption. In historic times, we have seen really little of them, while this is what we may still see of volcanic eruptions. And you can see here it's really huge. The Eyjafjallajökull eruption, which caused the shut-off of the airplane traffic of a large portion of Europe, is about here. It's nothing. It's really a small spot over the scale. So this gives you an idea of what we're talking about. Yeah, there are, of course, many factors that control the impact of volcanic supereruptions, and they are extremely complex and they play in very nonlinear ways. So some of these factors are reported here, and I would stress the strong nonlinear dynamics which take place in the atmosphere, so that fully understanding what the impacts of a supervolcanic eruption would be, a volcanic supereruption would be, is not easy at all. It requires a lot of microphysics coupled with a lot of global dynamics, and that's certainly not easy and still not definitely resolved. So there's a lot to do here. But no matter what exactly will be the effects of a volcanic supereruption, we know that they will be very, very large and substantial. This is taken from a report to the Geological Society of London by Steve Sparks and Steve Sells, and I would invite you to read this together. So supereruptions are different from other hazards such as earthquakes, tsunamis, storms, or floods, in that, like the impact of a large asteroid or comet, the environmental effects threaten global civilization. Our present civilization depends on global trade and food production, with much reliance on air travel and spaceborne communications, all of which could be at considerable risk if a supereruption occurred. An area the size of North America or Europe could be devastated, and pronounced deterioration of global climate would be expected for a few years following the eruption. Such events could result in the ruin of world agriculture, severe disruption of food supplies, and mass starvation. The effects could be sufficiently severe to threaten the fabric of civilization. Sooner or later, a super-eruption will happen on Earth, and this is an issue that also demands serious attention. While it may be in the future possible to deflect asteroids or somehow avoid their impact, we know of no strategies for reducing the power of major volcanic eruptions. So this is what we're talking about. We're talking about something that happened many times in the past. It will certainly happen again in the future, and it will have these consequences. So one big question is, can we foresee the occurrence of a volcanic super-eruption? And if we go to the literature, we see that there is a widespread belief that we probably can. What you can read or extract from the literature are beliefs such as an eruption of the globally impacting scale will be characterized by abundant and obvious precursors activity. And the time scale and types of super-eruption signal can be extrapolated from those of the eruptions that we know, and therefore will be accordingly bigger. And therefore, humankind should not be taken by surprise. These are common beliefs that we can find widespread in the literature. However, this might be questionable, and I would discuss that a little bit today. And surprisingly enough, some information about that comes from the distribution of global volcanic eruptions on Earth. That distribution has been studied in some detail recently, and as you can see by myself, also by others, of course, but this comes from one recent work by myself. And we now know that over the global scale, volcanic eruptions distribute like this curve here and this curve here. This curve here reports the the return time of volcanic eruptions, and the black line that you can see superimposed here and there is the theoretical curve for an exponential distribution. And as you can see, all volcanic eruptions on Earth follow very much an exponential distribution of their return time. The exponential distribution, in turn, is the characteristic signature of Poisson distributed events. So volcanic eruptions over the global scale are Poisson events. And these have some interesting consequences over the global scale. Well, this is how, if we go and see the return times of many volcanic eruptions, this is for the scale VEI7, like the Tambora eruption. We see that there have been many in this history of time, even going back again. But if you look at this distribution, you see that it's quite weird. There are periods characterized by very different slopes separated by hiatus, and people have fooled by these distributions in the past. This is for VI8. You see again apparently many different distributions separated by periods where nothing happened. People have been fooled, and that's because our mind is not prepared to understand and see immediately distributions which are as simple as an exponential distribution, but which reveal themselves in distributions that appear like this one. We normally tend to see normal distribution. Normal distribution seems to be well established in our mind, so that when we see this, we immediately see these trends that will be similar to those which will be produced by different normal distribution. And we completely fail to see the exponential distribution, which instead links all of this data. And you can see that, once again, here the black spots are the observed data for VI3, VI6, VI8, as you can see here, and the colored spots are random simulations that I did once I know the exponential distribution with just one parameter. So there is just one parameter that is enough to reproduce the very complex, apparently inexplicable distribution of return times of all volcanic eruptions in the world. So once we know that, once we understand that this apparently confused distribution are instead very clear, and they are very well described by a Poisson distribution of the events or an exponential distribution of their return times. We can therefore compute the rate parameter here, which is just one parameter, the only parameter that you need to describe the distribution. Just one parameter you describe the distribution. This is the mean and the variance in the rate parameter for VEI scale from 0 to 8. 0 will be very quiet lava flow, say it will be volcanic super-eruptions. And you can see here, you can translate these in a mean return time. But once again, we have to be careful. This is a mean return time over an exponential distribution. It doesn't have anything to do with the mean we are used to think at when we imagine a normal distribution, a Gaussian distribution. This is an exponential distribution which does not produce a value with some random oscillation around that. It produces instead that kind of complex distribution, apparently weird and unrelated that we have seen before. That's exactly what exponential distributions do. So if we know that, now we can say something about volcanic eruptions, again, at the global scale. They are Poisson distributed, and one fundamental characteristic of Poisson distributed events is that they are memoryless. What does that mean? It means that the probability of observing a next event, it is always the same. That's irrespective of the time since when we observed the last event. If a super-eruption occurred yesterday, the probability of having it again today would be the same as 1 week ago, because these events are completely memoryless. And the consequence is that when we refer to the global scale, there is no overdue event. No matter if we haven't seen a super-eruption for 100,000 years, it's 26,000 years now that we don't see that. No matter that, the probability of observing that in a specific time frame remains always the same. Therefore, there is no overdue event, which is a concept which sometimes appears in the literature. That's nothing to do with how volcanic eruptions appear and distribute at a global scale. And if we know the distribution, what we can do now is to compute those probabilities of occurrence. And that's what we have done here in a recent paper in Science with Vano Mazzocchi. And here I have highlighted the 6, 7, and 8 VEI explosive eruption, with 7 and 8 being those with global impacts, with more relevant global impacts. And as you can see here, we have the 1 year, 10 year, 100 year, and so on, probability of occurrence of volcanic eruptions of any scale. And if you look at VEI-8 eruption, the volcanic super-eruption, the probability, the 1 year probability of observing that is 1 out of 100,000, or 10 to the minus 5. And that's definitely, I would tell you, not trivial, not too small, not negligible. If we compare that with other 1 year probabilities that we know from other adverse events, for example, this is the maximum accepted 1 year probability for a nuclear reactor core melting, which is of the same order of magnitude, but actually in the practice, you cannot build a nuclear reactor if you don't demonstrate that the probability of core melting is lower than 1 out of 1 million, which is 10 times lower than a volcanic supereruption. You couldn't build a nuclear reactor if the probability of having core melting will be that of having a volcanic supereruptions on the Earth. So you understand the probability of a volcanic supereruption is not that small. And even more, if we compare with the 1 year probability of impact with a kilometer-sized asteroid, which is also 10 times less. And as we know, NASA is spending a lot of money, I would say correctly, to defend ourselves from the bad consequences from the impact of a giant asteroid, or kilometer-sized asteroids. But that's an event which has consequences which are not dissimilar by those of a volcanic supereruptions, but they are 10 times less probable. So volcanic supereruptions are really something we should care of. And if you look at 100 years, the time span of the life of a person, there is 1 out of 1,000 probability, what chances to see a volcanic supereruptions. That's more or less the chance we all have to see a volcanic supereruption, 1 out of 1,000. Not that small. And if we also add VEI 7 eruptions, which also have huge global impacts, we see that over the lifespan of a person, 100 years, the probability starts to be measured in percents. So the chance we have to see some global devastating impacts by volcanic eruptions is definitely non-negligible. And we also do something with this information. We can compute the rate of magma production at a global scale that you can see here over different time spans. And the distribution obviously changes a lot according to the time window we are looking at. And this is a kind of information which is definitely useful for crustal formation, plate tectonics, but also for studies on the role of volcanic forcing on climate change, of course. And we can do something more. We can put ourselves the question, well, now, assume there will be an eruption. What will be the probability of seeing an eruption with a certain size, which is a kind of a constraint probability. It's different from the absolute probability we've been looking at before. This is a constraint probability. So we see we can do the calculations, which is quite straightforward. We can do that in different ways when we have the information. And we see something which is good, which is that more than 99% of eruptions on Earth have VEI 4 or less. So that's good to know. We're comfortable with that. But we also see something that is less comfortable. If we look at the distribution of all explosive eruption from VEI 3 to 8, we see that they distribute according to a power law. And a power law is something which is very interesting when we see that in natural phenomena. Power laws occur in a variety of natural processes, and the paradigm, which has been extensively studied by a generation of scientists, I would say, is a sand pile. If we accumulate sand over a pile very slowly like this, we get to a critical stage when the addition of some more grains of sand will cause a collapse. If we observe the collapse and plot their frequency, we'll obtain something like this trend. So in most cases, the collapses that we see, they will be very small. In some cases, they will be a little bit larger. In some, even a few cases, we will be large collapse, and sometimes, in very rare occasions, we will see the complete collapse of the pile. And that happens according to a distribution like this one, which is exactly a power law. And a power law of this time comes from the fact that the processes, the physical processes subtending the occurrence of landslide in the sand pile are completely nonlinear and unpredictable by a deterministic point of view. That is because the grains which are involved are too many, and the conditions and the processes depends too largely from small, tiny details that even if we knew them with a certain accuracy, we will always discover that we need more accuracy in order to get closer with our prediction. So there is no way to deterministically predict these processes. There is only a way to predict them statistically. And that's what happens when we have power law distributions in nature. Power law distribution occur, as I told you, in a variety of natural phenomena. And in the geophysics, the most famous is certainly the Gutenberg-Richter law for the relationship between magnitude and frequency of seismic shocks. And to this, we are now able to add also the magnitude-frequency distribution of global explosive volcanic eruptions, which is also a power law. So power laws will manifest themselves in phenomena which will be scale invariant and self-similar. What does that mean? It means that if you look at the phenomena of a different scales, they are exactly the same, but they will be just scaled up to bigger sizes. That's the distinctive characteristic of power law phenomena. And here is scale invariance and self-similarity in volcanic eruptions. over 4 orders of magnitude here, from VI3 to VI6. They are exactly the same processes, same characteristics, same deposits, whatever similar, except that they are scaled up. That's the only difference. We don't have pictures for VI7, VI8, of course, eruptions, but we know from the deposits that their processes, their characteristics were all the same, that the smaller eruption we see, just they are much, much bigger. That's the only difference. So it's, I would say, I'm saying that, but I need to add that it's quite difficult to say if really volcanic systems are critical systems like a sand pile which evolve toward a non-predictable critical states. It's really difficult to conclude that, and I am completely aware that much more investigation is needed in order to say something more robust about that. What we can certainly say is that if volcanic systems were critical systems, we would see a power law relationship between magnitude and frequency, which is exactly what we see, and we would see scaling variance and self-similarity, of their products, which is also what we see. Yep. Because I have to go fast, I would say that power law, critical systems for critical state for volcanic system would question our capability to determinately predict the size of what happens. So I think it's at least important that we consider this information and we mind about that. It might be uncomfortable, but we might see in a condition where we may need to accept a limit in our capability to predict the size of a next eruption. And as a matter of fact, we don't have any general means of predicting the size of a volcanic eruption starting from what we see before a volcanic eruption. There have been many suggestions, many ideas, many hypotheses, but no generally accepted, no general means to relate them. So this might not be a limit in our understanding. This might also be a fundamental characteristics of volcanic eruptions. So I think it's important to talk about that. I will skip this, okay, because I think we need to go straight to the end. So supereruptions, what we know that it will happen again, and we know the probabilities with which it will happen again, and we know they are non-negligible, and we know that it will cause complete destruction of a huge areas, maybe as large as these, global disruption of food and economy, and profound political instability worldwide. We need to know much, much more about the gases which are ejected during volcanic supereruption. Sulfur and other allergens are mostly responsible for the global effects on the climate. And we know something about that, but I would argue that we know too little about that, and there is something more that we need to do. And this is something that I really like to talk about, but I had to cut it off because of time reasons, as you know. And what we instead may never know if some of these distributions that we have seen recently have some real consequences on the way volcanic eruptions occur on Earth. What we may never know is when it will happen, where it will happen, and the kind of signals that will precede them. So what to do? And this will be my last 2 slides. What to do, and I will go back to the report by Sparks and Sells saying that preparedness is the key to mitigation. And definitely we need to do much, much more on the scientific point of view. We are starting to understand many things about volcanic supereruptions. We are still models which are controversial, not exactly agreeing one to the other, so we have to expand our understanding of volcanic supereruptions, but also we have to do something more on the societal point of view, I think. This claim appeared only 3 months ago, and it's another warning. Catastrophic supervolcano eruption could push humanity to extinction. that's quite a bold statement, I would say, maybe a bit too bold, but I understand this is the kind of statements that national agencies do when they need to justify use of funds in front of the public opinion. So I expect that there will be something happening along this direction by large agencies worldwide. I expect our US colleagues to have more information about that. I should say that at the European level, there is probably not the same awareness of this kind of problems, but the ground is ready for an action at the European Commission to solicit their attention towards this kind of big, huge, immense risk for humankind. And this is also the renewed NASA attention on supervolcanic eruption is also pushing something more like this report from the Jet Propulsion Laboratory defending human civilization from supervolcanic eruptions, where they start to think at the possibility to engineer a supervolcano in order to impede the occurrence of volcanic supereruptions, or at least reduce its size, which is something that reasonably looks very, very distant by now, but it's good that someone is starting to think at that, mining at that. I mean, in some time we may come out with some solutions that we didn't imagine today. So that's the way how human understanding goes on. You always have to ask yourself something which is beyond, and then you progress in some way. But what I really think it should be done is to develop a global resilience plan for this. And a global resilience plans will be mining about how to ensure all this. We know that there will be a big impact on the capability of the world to produce food. Food reserves by the world now are enough for about 3 months, which is far too little compared to what we might have to face if a super-eruption would occur somewhere in the world. And we have to ensure the capability to keep on trading, transportation, communication, and so on and so forth, and whatever is needed to ensure the safeguard of the critical nodes and the elements which are necessary to defend the level of progress and civilization that humans have achieved. And that's all. Thank you.
Thank you very much.
I'm not famous for being short.
So if you have a very quick question. Yeah.
Yes, sir. Thank you for your very interesting talk. I want to press you on a specific question. So if we take a particular volcano, say Mount Rainier or Mount Fuji, to name 2 famous ones, you're saying the probability of a severe eruption follows a Poisson distribution independent of any experience or knowledge that we have of current previous eruptions.
Yeah, I've been quite careful to stress always, anytime I talked about distributions, that they hold at the global scale. When we go to an individual volcano, things might change a lot, and actually I would expect them to change. I wouldn't expect an individual volcano to be memoryless. A volcano knows in some way its previous history, an individual volcano. So the Earth as a whole is memoryless. So when we're talking about volcanic supereruptions, we are not interested in knowing exactly when they happen, where they happen. We are interested in knowing if they happen. So the Poisson distribution, the memoryless properties, these are relevant for them. When we are studying an individual volcano, things might be very different, in fact.
Okay, thank you. Brief? No. Okay,
Dr. Papale, do you think this would hold on the regional scale, though? These laws, the power law and the Poisson recurrence time. Do you think they might hold for regional volcanic systems, Taupo, perhaps Italy, perhaps South America?
Thank you for that. That's a very interesting question. And in fact, after the global scale, what I want to do is to start investigating the regional scale and also the individual scale. I mean, there are when you scale down, you lose a lot of information because the amount of information we have is much less. Therefore, you have to rely on other statistical means of comparing the small data sets with the distributions that you get from the large data sets, which is not necessarily trivial. But that's something that I want to explore, definitely. I don't have any answer for the moment, but definitely it's something that is in my plan.
Okay. Thanks for the amazing talk. I have maybe it's more of a comment than a question, but I think Tim Dritt and collaborator recently published, like a few years ago, the timescales of magma accumulation prior to volcanic eruption, and they found that the accumulation of magma could happen in like a decade, and so that kind of relates to like the recurrence of these types of eruption that we previously thought to be on the timescales of like thousands of years, or even like hundreds of thousands of years. So how could you implement this type of data in your probabilistic models?
Well, my specialty actually is to be a determinist. What I do all the time is to model volcanic system and trying to find deterministic relationships between quantity. So it's a bit weird for me to talk about all these statistics. And I've been asking myself, of course, how these concepts might translate into a mechanistic view of the volcanic system, including timescale of magma accumulation, the capability of a volcanic system to produce very large eruptions like those. We have started to do some numerical simulations of this system, and we think we are starting to find some of the major physical aspects that may represent mostly the sources of non-linearities, of big non-linearities that may give rise to relationships like those that we've been looking at, like the power law, for example, distribution of magnitude versus frequency. So definitely, yes, the mechanistic view of volcanic system is fundamental, and if these trends have a real meaning somewhere, we should be able to find some explanation by looking at the mechanistic picture of volcanic systems. So exactly what you mentioned, magma accumulation, timescales of magma storage and evolution, dynamics of volcanic eruptions in composite plumbing systems. That's very important. We are used to just look at shallow magma chambers and their eruption dynamics. I think we have to move on to a paradigm shift. We have to look at volcanic systems like complex systems, composite systems made of deeper parts, shallower parts, which are all interacting during a volcanic eruption. So it's a long way to go, but definitely very, very, very interesting and exciting.
Thank you.
Thank you, Paolo. Thank you, everyone.
Thank you.
Thank you.